In the quiet vacuum of space, a visitor named 3I Atlas is gliding past Mars. At first glance, it looks like just another comet. But something is wrong, and scientists at Harvard are getting alarmed. Despite raging jets of gas bursting from its surface, its trajectory barely shivers. This points to a startling conclusion. 3I Atlas is staggeringly massive. We're talking over 33 billion tons, with a nucleus the size of a mountain. That's orders of magnitude beyond anything we've seen from previous interstellar visitors. So if Atlas is so active, why is it so immune to the forces that shove ordinary comets off course? And if the mainstream explanation doesn't quite fit, what on Earth or beyond it could we actually be looking at? Pinpointing the true path of an object like Atlas begins with a discipline that's as much art as it is science: astrometry. Every night, telescope operators around the globe lock onto this faint speck of light against a shifting grid of background stars. The goal sounds simple: measure the comet's exact position in the sky down to a fraction of an arcsecond. But the execution is anything but simple. Modern digital detectors, known as CCDs, capture the faint glow of Atlas's hazy coma and pinpoint its center of light with astonishing precision. For the best-equipped observatories, a single exposure can give them a positional accuracy of a few milliarseconds. To put that in perspective, that's less than the width of a human hair seen from a mile away. But no single measurement stands alone. Each image is meticulously cross-referenced against a vast catalog of reference stars, which have themselves been mapped by missions like Gaia to an accuracy that would have seemed impossible just a decade ago. The process is incredibly detailed. Telescope clocks are synchronized to Coordinated Universal Time, or UTC, and every single exposure is tagged with the precise moment it was taken. Even a tiny error, like using local time instead of UTC or referencing an outdated star catalog, can nudge the apparent position by a measurable amount. To guard against this, teams apply statistical corrections, constantly recalibrating each night's data against the latest star charts. They even flag any observatory that consistently reports outlier positions. The result of all this work is a timestamp trail of Atlas's journey across the heavens. Each data point is the product of careful alignment, calibration, and error checking. So, when astronomers talk about trajectory residuals, those tiny differences between where Atlas is expected to be and where it actually appears, they relying on this rock-solid foundation. Our confidence in later claims about its mass, its acceleration, or its rarity all rests on the bedrock of these nightly measurements. Without this mind-boggling level of precision, the story of 3I Atlas would be completely lost in the noise of the stars. Before any claims about Atlas's enormous size or mass could be trusted, the scientists at Harvard had to take on a task just as daunting as the observations themselves: purging the data of any hidden biases. The raw numbers coming in from telescopes all over the world needed to be cleaned, standardized, and made consistent. Only then could they reveal the true story. And when they were finally clean, the numbers told a story that few expected. By cross-calibrating photometric data from dozens of telescopes, analysts pinned down Atlas's apparent brightness across multiple nights and through different filters. This whole process hinged on a handful of key assumptions. First, the reflectivity or albedo of the nucleus. They bracketed it between 0.04 and 0.06, which is in line with some of the darkest, most soot-covered comets ever measured. Then they considered a plausible range of densities, from porous, fluffy ice to denser, rockier mixtures. When they plugged those values into the standard equations, the math pointed to a nucleus pushing 5 kilometers or over 3 miles across. Now, that's not just big for an interstellar visitor, it's big, period. Most comets that swing through our inner solar system are just a fraction of that size. Even the famous comet Bernardinelli-Bernstein, nicknamed the Monster Comet, is only slightly larger, but here's the real kicker. The force calculations derived from those tiny trajectory residuals and the observed coma didn't budge that estimate one bit. The measured non-gravitational acceleration, the push from the gas jets, was less than 15 meters per day squared. That's so incredibly small that, for the observed level of outgassing, only a body of immense mass could resist being nudged off course. The numbers all converged on the same answer. A nucleus at least several kilometers wide with a total mass exceeding 30 billion tons. It's a result that held up under every single permutation the analysts threw at it. They ran Monte Carlo simulations, they tweaked the density values, they even tried alternative force models. Each and every time, the lower bound estimate for its mass stayed stubbornly high. For the first time, the interstellar comet catalog had a true heavyweight contender, and the implications of this discovery began to ripple through every corner of the research community. Shock hit the Harvard Working Group before dawn. The final mass figures had barely been circulated before their internal Slack channels flared with disbelief. In the world of interstellar objects, size is everything. And Atlas's numbers didn't just break the curve, they completely shattered it. For context, every other interstellar object cataloged so far, like Oumuamua and Borisov, were cosmic pebbles by comparison. They were small enough to be flicked off course by a gentle puff of gas. But Atlas, at over 30 billion tons, stood utterly alone. It was in a class of its own. The prevailing models, which were built on years of survey statistics, predicted that such a massive, active interstellar object should be vanishingly rare. In fact, they were so rare that some theorists argued we might never see one in a human lifetime, and yet, here it was. Within hours, the crisis spilled beyond the walls of Harvard. Emergency teleconferences were set up, drawing in teams from NASA, the European Space Agency, and the Minor Planet Center. The numbers were double-checked, then triple-checked. The data was scrutinized, the methods were debated. But the result remained the same. Atlas was a giant. The discovery raised a fundamental question. Was understanding of the universe wrong, or was 3I Atlas something more than just a comet? The debate is still raging. Some scientists are exploring more exotic explanations. Could Atlas be an object with an unusual composition, making it far denser than a typical comet? Could it be a fragment of a larger shattered world from another star system? And then there are the more speculative ideas. While highly unlikely, some have even quietly wondered if its resistance to outgassing could hint at an artificial structure. For now, these are just questions. But one thing is certain, 3I Atlas has forced us to reconsider what's possible. It's a reminder that the universe is far stranger and more surprising than we can imagine. As telescopes continue to track its journey, every new piece of data will be scrutinized, hoping to unlock the secrets of this mysterious interstellar visitor. What will we find? Only time will tell. The tension was obvious in every exchange. Some called for caution, raising the specter of hidden biases or unmodeled physics. Others, more blunt, called it the most improbable find in decades. By the end of that first week, the consensus was less about what Atlas was and more about what it wasn't: ordinary. The field had been handed a puzzle that defied the numbers, and the search for answers was only just beginning. The debate around 3I Atlas's true nature now plays out across a spectrum, from what's firmly established, to the plausible but unproven, to the outright speculative. In his simulations, young star systems don't just sweep up local dust. They act as cosmic nets, capturing stray interstellar objects that wander too close. The logic is simple. More massive stars build larger, denser disks, and their gravity reaches farther. Theoretically, this gives them more chances to snare passing bodies like 3I Atlas. But when Falsner's models are scrutinized, the optimism fades. The capture rates do climb with stellar mass, but the numbers are still small. Even in the most favorable scenarios, only a handful of interstellar objects are expected to be trapped during a disk's short window of opportunity. Peer reviewers poring over the simulation outputs question whether the known population of objects this size is anywhere near enough to make a difference. One reviewer's comment, leaked from a 2025 submission, stated, "The premise is elegant, but the statistics are not on its side. The broader astrophysical stakes are clear." For now, the planet seed idea sits in a liminal space, imaginative, mathematically plausible, but lacking the hard numbers that would turn a trend into a law. The countdown begins in earnest as 3I Atlas sweeps toward its next rendezvous. Mission planners across 3 continents have circled 4 dates, each a window of opportunity and risk. First, early October. Mars Express and the ExoMars Trace Gas Orbiter, both orbiting Mars, will train their instruments on the visitor as it passes within millions of miles of the red planet. Atmospheric spectrometers designed for Martian weather will now hunt for faint traces of water, carbon dioxide, and metals in Atlas's coma, hoping to catch the first chemical signatures from outside our solar system. Late October brings perihelion, the moment Atlas swings closest to the Sun. At this point, ground-based telescopes lose sight as it vanishes into the solar glare. Only spacecraft with the right vantage point can monitor its activity. Finally, in March 2026, Atlas is projected to skim above Jupiter's cloud tops, possibly within 33 million miles. NASA's Juno spacecraft, already in a polar orbit, may be retargeted to sample dust streams if mission controllers approve. Each milestone is a test of instruments, of planning, and of the theories that have built up around this extraordinary traveler. Every research team now keeps a live checklist, a watch list of measurements that could break the tie between natural and exotic origins. At the top of that list are isotope ratios in the coma gases,